Hello everybody, welcome back to another video, and in this video we'll be looking at taking the derivative of the inverse cosine of x, and here we'll follow a pretty similar set of steps to the first video I made when looking at the derivatives and integrals of inverse trigonometric functions, where we looked at the derivative of the inverse sine of x. So here we're looking at the derivative of the inverse cosine of x, and in my previous two videos we looked at the derivative of and the integral of the inverse sine of x. So let's get started with this. So what we do is we see that we can set up some function y to be equal to the inverse cosine of x. Now what we know is that if we just take the cosine on both sides, so if we take the cosine of y and the cosine of the inverse cosine of x, I'll just write it like this, we see that taking the cosine of the inverse cosine of x, by definition that will just return x, or the input more generally, because when you have a trig function applied to that inverse trigonometric function, you will always return whatever that input is. So we see that we get the cosine of y now, because we're taking cosine on both sides, is equal to and just x. Now what we do now is we can set up a system where we want to find, of course, dy by dx, and we are trying to set up a system to isolate dy by dx. And what we see is that taking the derivative immediately in this first step on both sides, on the left hand side we take the derivative of y with respect to x, which is dy by dx, and on the right hand side we have to take the derivative of the inverse cosine of x, but we don't know that, and that is circular reasoning. So what we have to do is we needed to do this step in order to get it to something where we can differentiate both sides. So now what we can do safely is we can take d by dx on both sides, like so, and taking the derivative of, let's just do the right hand side because it's easier. So taking the derivative of x with respect to x is just 1. Now taking the derivative of cosine of y, we see that we have, because y is not a constant, y is another function of x, we have a function inside of a function, and that is for the chain rule. That calls for the chain rule. And the chain rule, we know that we take the derivative of the outside function, then we have to multiply by the derivative of the inside function. So what we have is we have the derivative of the outside, the derivative of cosine, which is negative sine of y. So we just have negative sine of y. But remember, y is a function of x, so we multiply by the derivative of y with respect to x, which is dy by dx. So now all we need to do is we need to isolate dy by dx. And how do we do that? Well, we just need to divide by negative sine of y on both sides. So divide by negative sine of y. So what we see finally is that dy by dx is equal to the negative of the, or that's equal to 1 over, and then we can put the negative here, and then we can put the sine of y. Now what we now can do is we can utilize the relationship between the sine and the cosecant, namely the fact that they are the reciprocals of each other. So 1 over sine is just going to be the cosecant. So we see that dy by dx is, or let's just write this a bit more nicely, we see that dy by dx is just equal to, we still have a negative there, and then we have the cosecant of y. Now we know that y, our original function of y, was the inverse cosine of x. So we can write that here and get everything in terms of x. So we see that dy by dx is equal to, we have negative, and then we have the cosecant of the inverse cosine of x. Now, what we can do, we can apply a method where we see we have an expression in the form of a trig function applied, and then on the inside we have an inverse trig function. And whenever we have a structure like this, always what we need to do is we need to construct a triangle often, and then find out what the operation of the side lengths is. So what I mean by that is that we have the inverse cosine of x. Now we know the inverse cosine of x takes in a ratio of two sides. Namely, it takes in the ratio of the adjacent to the hypotenuse, because we know that the cosine is the adjacent of the hypotenuse. So taking the inverse cosine will take in the adjacent divided by the hypotenuse and spit out an angle. Let's say we have theta. So let's make a triangle now, because we know that if we're taking the inverse cosine of, and then we have two side lengths, we know that those must be the side lengths of the triangle. So let's say this angle here is theta. This is a right angle triangle. The inverse cosine means that the adjacent of the hypotenuse is x over 1. We know that x is the same thing as x over 1. So the ratio must be x and then 1. And then by Pythagoras, we know that this missing side must be the square root of 1 squared minus x squared, which is just 1 minus x squared by Pythagoras' theorem. So what we need to do now is we just need to see that we have constructed a triangle now using the side lengths given to us by this inverse trigonometric function, and we have an outer function being applied to now that theta, because we know that this inverse trig function returns an angle theta. And now all we're doing is we're taking the negative cosecant of theta. And what is the negative cosecant? Well, that's 1 over sine, so that means it is the hypotenuse over the opposite. So what we see finally is that the dy by dx is just equal to negative, and then we have the cosecant, which is the hypotenuse, which is 1 over the opposite, which is indeed the square root of 1 minus x squared. And this is our final answer, and this shows how we can always simplify a trig of an inverse trig function. And there's in fact images with tables that are very helpful to use when you need to do these. So what we also notice is that this happens to be the negative of the derivative of the inverse sine of x. So if we scroll up, we see that our derivative of the inverse sine of x happened to be 1 over the square root of 1 minus x squared. And here, the derivative happens to be negative 1 over the square root of 1 minus x. And to really see why this is the case, we can look at this with a very nice identity, and this all fits really well, and we get to see why this is really the case. So what we see is that we know the identity that the inverse sine of x plus the inverse cosine of x is pi over 2, but let's prove that really quickly. So let's say we have some inverse sine of x to be equal to some theta. And because we know that the inverse sine of x will return some angle. Now let's take the sine on both sides using the same idea that the sine of the inverse sine of the input will just return the input. And taking the sine on both sides will mean that we get sine of theta, and that's equal to just x. Now what we can do is we can rewrite the sine of theta as the cosine of pi over 2 minus theta. We know that because they are co-functions, and the sum, and what we can do is we can know that if we're taking the cosine of, for instance, 30, that's going to be, or the sine of 30, that's just going to be the cosine of 60, because they're complementary. That's why it's called cosine, because the angles add up to 190, or pi over 2. So here, if we take this and rewrite this as the cosine of pi over 2 minus theta, that's equal to x. Now what we see is that here we can take the arc cosine on both sides, and taking the arc cosine on both sides, we see that we get the inverse cosine of x, and that's just equal to the inverse cosine of the cosine. In this case will cancel because we have something less than pi over 2. So here we have a pi over 2 minus theta. Now, what happens when we add the inverse sine of x and the inverse cosine of x plus the inverse cosine of x? Well, that's just going to be equal to, well, inverse sine of x is theta, and inverse of cosine of x is going to be pi over 2 minus theta. And, well, what happens here? This and this cancel, and you're just left with pi over 2. And this is the case with all co-functions. For instance, the tangent and the cotangent. What we'll be doing is we'll now be seeing that using this identity. So here we'll just write this. Let's just make this all a bit smaller. And now let's say we write the identity out. We have the inverse sine of x plus the inverse cosine of x is equal to pi over 2. Now let's say we now take the derivative on both sides. So that means we take d by dx on both sides. Now when we're taking the derivative of the sum, that's the same thing as the derivatives of each element in the sum. So this is the same thing. So we're saying the derivative of the inverse sine of x plus the derivative of the inverse cosine of x, and let's just compute the derivative of pi over 2. Derivative of a constant is always 0. So we have 0. And what we see here very nicely is that we can rearrange the equation, subtract d by dx of cosine x on both sides. We see that the d by dx, the derivative of sine x, is just equal to, then we have the negative d by dx of cosine inverse of x. So what we can do is we can use this idea where we don't even have to work out, we can just work out one of them, and then from this relationship we can find the derivative of the other cofunction, which I think is pretty cool. So anyways, that was it for today's video, and thank you for watching.